Hi, welcome to Lecture 2 of Biomechanics 1. When a load or force is applied to an object, the possible consequences would be translation. So the object moves from point A to point B, or the object will rotate, and lastly, it could deform. Now let's concern ourselves with deformation. We need to take into account the dimensions of the object. So I have here two pictures. One is spider silk, which is more biological in nature, and the other is a dental floss, which is more of a household material. Okay, we are often told that the spider silk is strong, but by experience, a strand of spider silk can be more easily broken compared to that of a strand of floss. So why is that? So the difference is that floss is much thicker than your spider silk. If you take a bunch, for example, of spider silk with a total thickness equal that to the floss, then it would be more resistant to breaking than your dental floss. Now consider this object, okay, and let a force F, okay, so let me put a pen here. So let a force F be applied, okay, normal to a pair of opposite faces. So this is your pair of opposite faces, and the force is applied normal to these faces. So when I say normal, it means perpendicular, okay? Now, to compute force stress, all right, so stress or nominal stress is actually applied force divided by the original cross-sectional area, okay? And it's also called engineering stress. We call it nominal because the actual value of the area will change in response to the load, di ba? So kapag nag-apply ka ng load, yung area dito, magbabago yan. Okay? Depending on if you apply these forces as tension or compression. Okay? So the stress that you will compute from that is called your true stress. Okay? But that's very difficult to compute because again, the area will change. So that's why we resort to computing what we call the nominal stress. You take the ratio of the load and the original cross-sectional area. And as you can see here, there are other types of stresses aside from normal stress. So again, normal means perpendicular to the face. Normal stress could be either tensile or compressive. Okay. Aside from normal stress, we could have shear stress as well. Wherein the shear stress, okay, the force is applied, okay, sort of parallel to the area of application, just like you're seeing here. So the deformation, okay, is something like this if you have your shear stress. Okay, so unlike your normal stress, na yung deformation is either the object will contract or will elongate. It's also possible that in an object, you apply both shear stress and normal stress. So it's also possible that your stress will have normal and shear components, just like what's being shown here in this third picture. So in computing force stress, okay, the shape of the material can be ignored. Okay, so it doesn't matter if the material or the cross section is circular in nature or square or whatever geometry that you have. Okay, all you have to do is get the total cross-sectional area of that material in order for you to compute stress. So stress again is simply force per area, or F over A. And the area we're considering again is your cross-sectional area. And typical units would be maybe Pascal, or that's equivalent to Newton per square meter. Okay. Megapascal can also be used, or gigapascal, or you can actually use pounds per square feet, and so on and so forth. Okay. Now, aside from stress, we can also calculate the amount of elongation, okay, of a certain material relative to the original length of that material. So L here is the final length of the material. For example, so if you apply a certain load, it will elongate or contract, okay, up to a certain length. Okay, get that difference between that and the original length and divide it by the original length. So we call that strain. Okay, and we are going to use the symbol epsilon for strain. And as you can see here, strain is dimensionless or unitless, okay? Because both the numerator and the denominator would have dimensions of length, so they just cancel out. Okay. Now, so we know that stress is force per area, okay? And we know also that strain is the change in length divided by the original area. If we're going to take a plot, or yes, plot stress in your y-axis and strain in your x-axis, the slope of the plot, okay, if it's linear, we call it the Young's modulus. Okay, Young's modulus. So this is a constant property which has something to do with the stiffness of a material. Okay, so the higher the Young's modulus, the stiffer the material is. So in other words, to get the Young's modulus, or sometimes we call it Young's modulus of elasticity, simply divide the stress and strain. So E equals sigma over epsilon, stress over strain. Okay, so again, Young's modulus is actually the slope of this line here, if this material being considered follows your Hooke's law. So in physics, Hooke's law is expressed as your force being proportional to the deformation. Okay, and K as the constant of proportionality is sometimes called the spring constant. All right. Basically, what Hooke's law means is that, okay, if let's say I applied some stress, okay, to a certain object, what will happen is that there will be an equivalent deformation. Okay. Now, if I remove that stress, okay, sorry, I remove that stress, for example, like that, okay, yung deformation, okay, ay babalik dun sa original. Okay, and that's because of the linear relationship expressed by Hooke's law. Okay, so that's also the case if you have the plot of sigma, okay, or stress, and your strain. Okay. So stress is the distribution of force over an area, while strain is a dimensionless measure of length change. And if you take the ratio of stress and strain, you will get stiffness, or Young's modulus. And it's the change in stress required for a change in strain. And again, it's the slope of a stress-strain curve. And I'm showing you here typical materials, okay, and their corresponding Young's modulus. And thus, we can say that The human bone, for example, is much stiffer compared to plywood, cheap plastic, and even the human tendon and the cartilage and others. Okay, and in this list, the diamond is actually the one with the greatest value of the Young's module. So meaning, among these materials here, it's the stiffest. Okay. Some biological materials have their lot of stress and strain illustrated here. So you have your bone, your hair, and your resilin. So as you can see, si bone, dahil mataas yung kanyang slope, therefore mataas yung kanyang Young's modulus. So it's very stiff, right? Hair is pretty stiff as well. Okay. It is said that the combined hair of a whole head could lift or support 2 tons of weight, or that is equivalent to 2 adult elephants. Okay. Now, resilin is a protein found in the hinges of arthropods, yung mga insekto, for example, okay, sa kanilang wings. And as you can see, it's quite well extended sa kanyang graph. That means that you can actually elongate resilin by this much kahit konti lang yung stress na na-apply. Alright? So ganyan lang ka-konti yung stress, but it's well elongated. Okay? And the reason is that they are present in, of course, the wing hinges in your arthropods. Now, the thing is that for most biological materials, okay, these materials are actually the case is that they are non-linearly elastic. So instead of having a linear curve here, okay, or a straight line, so hindi sila linear. And that is the case for most biological materials, such as tendon and even your hair. Okay, and that is possible because of some effect of the molecular structures in these materials. Here I'm showing you where to locate the resilin in the wing hinges of your insects. Okay. Okay. Now let's solve some problem involving stress. Okay, so you have here the human bone, which is composed of a shaft with 2 flared ends. Okay, so we call this part the diaphysis, and the flared ends are what we call the epiphysis. And the diaphysis actually resembles that of a hollow cylinder. A hollow cylinder material is being considered as a biomaterial for bone replacement and is designed to support a compressive load of 650 kilonewtons. The allowable compressive stress is 69.2 megapascal. Compute the outside diameter of the cylinder if the wall thickness is 50 millimeters. So what the problem says that in designing this biomaterial for bone replacement, we have predetermined that the wall thickness ought to be 50 millimeters, no? Dapat. Okay? Kung 50 millimeters dapat yung kapal ng wall, ng diameter, or ng cylinder rather, ano kaya yung size ng cylinder or the diameter of the cylinder? Okay? Since it's a hollow cylinder, all right, it will have a large diameter and a small diameter. Okay, so halimbawa ito yung cylinder for bone replacement for the diaphysis. And again, we want that this replacement should support a load of 650 kilonewtons. But the allowable stress for this material is 69.2 megapascal. And we want the thickness, so this is actually that. So this is the thickness, okay, to be 50 millimeters. Now in this top view here, okay, yung hollow view niya, okay, let's name the outer diameter as big letter D and the inner diameter as the small letter d. Okay, and this is now your thickness. Okay, so stress is the load divided by the cross-sectional area, or F divided by area of the big circle minus area of the small circle. So you need to subtract the area of the small circle, which is the hollow part, right, from the big circle, because the cross-sectional area is this portion only. Okay? Yan lang. Okay? So A big minus A small. Now, let's apply that formula. So F over the area of a circle is pi over 4d squared. Okay, so this for the large circle, this for the small circle. Okay, and simplifying that, it will become F over pi over 4 d squared minus small letter d squared. But we want to compute the diameter, okay, of the cylinder. So you have here two unknowns, right? But what we have is the thickness. So we need some expression, okay, to express the diameter as a function of thickness. So we know that this big diameter here, okay, is actually the sum of this diameter, small d, and twice the thickness, okay? All right, so inner diameter plus t, that will become d plus 2. And solving for small letter d, or the inner diameter, will have the outside diameter minus 2t. So we can plug that in here in this expression. Plugging in the known values, okay? 50 here is 50 millimeters, okay, just to show the units, then squared. Okay. And now the only unknown is d. And you can use your calculators and you will find out that the big diameter is 109.8 millimeters. Okay? So kung ang thickness niya ay 50 millimeters and twice that is 100 millimeters, okay, meaning it will have a very small inner diameter. Okay, just some comment about the units used here, okay. I use a unit of Newton for the force and yung millimeter or square millimeter for the area, okay. So would it be consistent with the megapascal unit here? So yes, actually megapascal, okay, is equivalent to Newton per square millimeter. Okay, these are equivalent. Okay, now let's talk about elastic deformation. So you have here an object and you apply some tensile force F. Okay, now it has an original length LO, and when you apply the tensile force, it has now a new length LN. Now, what if I want to solve for the change in length, yung delta L or Ln minus LO? Okay. We know that stress and strain can be computed as follows. So stress is force over area, and strain is the original length, the new length minus the original length over the original length. Now this numerator here, we can actually replace that with delta. Okay, and this delta, small letter delta here, represents the change in length or the deformation. Okay, now if we want to compute for delta using some other properties, so again, remember that Young's modulus is stress over strain. Substitute the expression for stress, F over A, and for strain, that's delta over LO. Therefore, if you want to solve for the deformation, you will arrive at this expression, which is very important in this subject. Okay. So let's try to solve this one. I have here a figure for a column of fatty tissue, and we want to know the strain, okay, in each of this of the three regions. Let me replace this with probably the deformation instead of the strain or the change in length. Deformation. Okay. So I have here a force 55 Newton. Okay. What will be the change in length in this section, in this section, and in this section? But I'm going to compute only for this section. And this section is actually a section of fat. Okay, so we're going to use the Young's modulus for fat as 18 kilopascal. The blue section is actually a tumor section, and the Young's modulus is 106 kilopascal. You're given here the cross-sectional area, 40 square centimeters, and you're given the length of each section. I'm going to compute only the deformation in this portion. Okay, so if you have computed the deformation for all portions, you can just take the sum. Okay, so for the first section, okay, so this should be fat. First fat section. So again, the deformation is FLO over AE. Let's just substitute the given. 55 newtons. Original length is 15 centimeters. That's 0.15 meters. Area is 40 square centimeter. That's 0.004 square meters. And Young's modulus is 18 kilopascal. So that's 18,000 Newton. I'm sorry, 18,000 Pascal. This should be Pascal. Sorry for that. And you will be able to arrive at an answer of 0.115 meters. So next we're going to discuss about the stress strain curve.